This is Professor Jimenez. Today we will see time delays in assembler code. And most instructions in PIC microcontrollers require 4 machine cycles, which form 1 clock cycle. In this class, we use the PIC 16F1618, which has a 4 MHz internal oscillator. And the frequency internally, it is divided by 4, resulting in a clock equal to 1 MHz. And the time period for 1 MHz is 1 microsecond. That is 1000 nanoseconds, okay? Thus, each machine cycle has a period of 250 nanoseconds. So this is how we do the division of the frequency oscillator by 4, and we get the 1 microsecond. And right here, we have the machine cycles. As I said, there are 4 machine cycles. This is one period, another one, so we can take it at the rising edge of the clock signal. So this is one instruction that requires 1 clock cycle, and each clock cycle from here to here forms 1 machine cycle. And this is another instruction. So this is the machine cycle and instruction cycles. To create a delay using nested loops, we will use the instructions decfc, go to, and move wf. So let's start learning how to create 300 microseconds, for example, a 200 microseconds delay in assembler code. So first we load W, the working register. We load it with a constant, with a decimal number 99. I will call this cycle TCY0. And so we just load this constant, this number, into this accumulator W. Then we move number 99. We move it to file 32. So move the contents of W to file 32. So number 99 decimal, it's loaded into file 32, which is a RAM location. Then now that we have this, we can start creating a decrement. So we will decrement, this is label X, we will decrement file 32 by 1 and store the contents in the same file. This is why you have here comma 1. So file 32 is loaded with the decrement of file 32 minus 1. So from 99, it'll go to 98, 97, and so on until it reaches 0, because it says decrement file and skip is 0. So if it is 0, it'll go here. But because it is 98, so after the decrement becomes 98, it'll go to X, to this label. So decrement file skip is 0. It's not 0, so it goes here because file 32 is different from 0. So go to X, and so it'll be looping right here 99 times. If we consider location 0 or count equal to 0, it'll be 100 times. So this instruction requires 2 clock cycles. According to the datasheet, the go to X requires 2 clock cycles. So two clock cycles here, plus the 1 clock cycle here, which I made a note here, 1 clock cycle. So we have 3 clock cycles from here to here. So 3 clock cycles times 100 times 99, we get 300 microseconds. And of course, you might consider that once the file, the register or file 32 reaches 0, the microcontroller, the program counter, will jump to this instruction, clear W, and that's another clock cycle that you might consider in your delay. And then we are adding an NOP instruction operation, which will add another cycle. So that's also, those are, sometimes we call it undesirable clock cycles, but if you really want to get a more accurate clock cycle because of this, then these 2 instructions, then you can decrement here by 98, or you can decrement it by 97, you see, until that way you will decrease the number of loops, and because of these added clock cycles. So the total period in this case is it's 300 microseconds because it was by 3. Okay, and of course you can add a 1 microsecond. So it was here K3. It was equal to well, I'm gonna leave it here as K3, but we know K3 is equal to 99. And because counting starts with 0 and not 1, from 99 to 0, it is equivalent to 100 clock cycles. So notice that the two previous instructions, move LW and move WF, also add an undesirable 2 microseconds delay. So you can also consider those. Okay, that depends on how you write your code, how you use it. Okay, and in this a flow chart, we have here the starting. I place here the word initial, but that means to initiate or starting point. So first you load the constant K1 into C1, which is a register, constant K2 into another register, K3 into another register. So every one of those requires 1 clock cycle. And then once you load K3, you have to start decrementing C3. So C3 minus 1 is loaded in the same location. And then you test it. Is C3 equal to 0? And no. So go to C3. So when you say no and this arrow represents go to, that's 2 clock cycles. Okay, 2 clock cycles plus this comparison using the decfszz instruction, that's another cycle. That's 3 cycles for this entire decrementing, or for this entire loop. We can say, yeah, we have 3 clock cycles. So once it is equal to 0, yes. So now you have to decrement C2, and then C2 is equal to 0. No, so go to the previous one to load a C3 again and do it the number of times you have here on C3. So and then you, once it reaches 0, you decrement the first register you loaded, and you ask to determine if it is equal to 0. No, another 2 cycles, and goes back to the beginning right here, and until the loops are finished. So this is the end, and you see we have nested loops because this loop is nested into another external loop, and these 2 loops are nested into another external loop for C2. So we have 3 nested cycles, loop cycles. The total number of executed cycles is as follows. So it's 3 times K1, K2, K3 plus K1, K2 plus K1 plus 1. And calculating the number of cycles, how to calculate them is done this way. Starting with the internal nested loop, we get the 3 clock cycles. Remember, there were 2 for go to and another 1 for the decrement. And so 1 for decrement, 2 for go to, and plus 1. Okay, the plus 1 is because in the beginning you are loading K3 with a constant, so that requires another cycle. And for the second register C2, you have that the second constant K2 times will perform the first loop C1 plus 3 clock cycles, and so on for C3, C2 plus 3. You see, so it is getting nested, and then you multiply by K1 plus 1. So to calculate each nested loop, we will see, for example, if we make K1 equal to 5, K2 equal to 255, K3 equal to 255, we get the time period as follows. So we follow the formula, the equation, 3 times K3 plus 1, so K3 is 255, so we get 766. For C2, we substitute the values, we get this number, 195,331, and then we substitute in C1, and we get this number, which is 976,656. So it's almost 1,000,000 cycles. And because of this formula, we have 976,656 cycles. So if we multiply this by 1 microsecond, we're almost approaching 1 second. So, and we have the total time, 4 cycles divided by the frequency of the oscillator. So we get 0.9766 seconds. Okay, and I'm leaving a homework for students, which you can check it on your group and on Canvas or another group that we are using. And you have to write the assembler code and show your calculations to create the following delays. Okay, so we have this number of delays. So you can see here that for this, the first delay, you only require 1 register, and just another register. But right here, you require also 1 register. Right here, I can assure you will require 2 registers. So you have to see how many cycles you can reach in every register, depending on the formulas that we saw. And that way you will write your code for this for this type of delays. Okay, that's all. Thank you.